Okay, now let's talk about fusing two tracks. Okay. Output on two tracks under the assumption that they are independent tracks. That is a big assumption. Okay. The track-to-track fusion, the main problem with this assumption. Simply, you can't assume they are independent. Okay. But a simplest case, let's assume independent and see how we go to the fusion. So if they are independent, so you can consider that like a normal track to measurement association. So you have a track here, another track here. Let's say at K, at time K, you have a one track here, another track here, another track here. So this has another track here. These are the inputs that you have for the track. Okay, so you want to associate that. So by looking at this, you can immediately say that okay, if I have IDs like this 1, 2, 3, and you say 1, 2, and 3. By looking at it, you can say that 1 and 3 goes together, 2 and 2 goes together, 1 is separate, 3 is separate. So clear? That's what you would say, right? By looking at it, this is a possible output that you have. So this is what we are going to do. This is similar to the measurement fusion, right? So you can consider blue as a track. You can consider this red as the measurement. Then we would do the similar approach that we do in the track to measurement association. We are going to do that for track to track association. Okay, how do we do that? So this one, this is similar to the S that we have. So in the normal track to measurement association, we had S here. Instead of S, we have this P1 plus P2. Okay. Instead of S, we are adding these two covariants and we have that. And delta, this D is similar to the innovation that we have. Right? In the normal Kalman filter. So when we do truth track association, we have the innovation S. Now, similar idea. So instead of innovation, we have the distance between two tracks. And this is the covariant. This is the normalized distance. As long as that's normalized distance less than some value, we say they are coming from that same target. Otherwise, they are not. Clear? If you understand track to measurement association, I think this is pretty simple. No different. Okay. So this is about associating the data. Okay. Once you associate the data, so now next is fusing, right? So like you know that like we have two problems to handle. This is track to track association is done now. As the next thing we are going to do, once you know that okay, these two goes together, final objective is to get this and this. That's objective, right? So I have one estimate here and the other one is here. We decided that both of them are coming from the same target. By fusing these two, I want to say that this is the updated state. Correct? That individually, that's what we want to say because the blue one says the track is somewhere here. The red one says it's somewhere here. Both are true, so it should be in the intersection. Right? So that so the black one comes somewhere here. Right? And the covariance is small, like the area is small. That is the idea of fusion. When you fuse, you reduce that covariance to a smaller value. Okay. So how we achieve this? So if you look at this equation, this P is, so you can use that or this term. Both will give the same answer. This one you can think as, I think when you studied about CRLP, you can think as inverse of covariance as information. So that new information is equal to the information that we get from sensor 1 and information we get from sensor 2. You add, that's the total information. You take an inverse, that gives the covariance. But this is true only if these two measurements are independent. But if there's a correlation, then this is optimistic. Okay? Okay, anyway, so this is the equation you would follow by the updated covariance for the state. So you are updating with this. So if you think this way, if you look at this, it's something like that, right? So if you look at this way, if the covariance of x1 is larger, we give more weight to the x2. Right? So you see that like with this denominator is the same. For x1, we have p2, x2, we have p1. Right? So if you want to think this way, if the covariance of x1 is larger, we go towards, we give more weight to x2. If the covariance of x2 is larger, then we give more weight to the x1. Okay, that is what we do. Okay. Okay, as a next thing, we are going to talk about fusion without memory and fusion with memory. I don't have any slides on this, but I will spend a little bit of time on that because this is an important difference. These others are clear, I believe. Synchronous and asynchronous, we already know from the name. Okay, thanks. Correlated case, I will talk about. That is a general case. In general, there is a correlation. Okay. So this is a simple approach. You can do that, but it's not okay. Okay. We'll talk about the correlated case later, right? So synchronous and asynchronous fusion mean, so if one of them are coming at the same time, that's synchronous. I said that won't happen. So usually it will be like that. And that is the asynchronous fusion. Okay. Homogeneous and heterogeneous means we are talking about homogeneous. Heterogeneous means maybe x dot y dot, and another person is giving r dot theta dot. This is called heterogeneous. But we don't know, like that's complicated. We are not going to talk about that. Right. Okay, now I am going to talk about the important part about fusion with memory and fusion without memory. Okay. Let's consider the case in which, let's assume first a synchronous case. Okay, you have the synchronous tracks here and here. Okay, so first let's talk about without memory. Without memory means, so let's say you have tracks from this and this, you fuse all of them and produce the output. Like let's say this is this. You get all the tracks and fuse, finally you get this. Okay, that's it. from this tracks and this track, you fuse all of them. You know there are two tracks here and there. You plot it. That's it. Then you don't keep anything in your memory. That's all. It's without memory. You don't have anything in the memory. Then you get the tracks again, and then you update. Okay. So then in this time, I'm going to update and say it's here and here. Third time when it comes here, maybe I update. It goes here and here. Okay. So this is called without memory fusion. So you don't save anything in the memory, plot it, forget, plot it, forget, plot it, forget. But you can't do simple without memory fusion is that because eventually you don't want to show the dots to the user. As a user, in addition to the dots, I want a connection. Right? That means connection means somehow you should be able to connect. Somehow you should be able to connect these and say one track, these are track two. That somehow you have to do it because if you do the memoryless fusion, then if you connect, how to connect is the harder problem. So that is why usually I don't use without memory fusion. Okay. But the good thing about the without memory fusion is that somehow you can assume the measurements are uncorrelated. But when it comes to with memory fusion, you are going to introduce highly correlated measurements. Okay, now I'm going to talk about with memory fusion. That's what I always use. Okay, I would recommend that. That means you have a tracker one here, that tracker two here, and this is a central tracker. Okay, all of them have track. This has track, this has track, that has track. In the without memory, this doesn't have any track. Whenever it gets fused, okay. Okay. But this can be handled in any asynchronous, synchronous case. This can be handled. Okay. So what happened right now is that to simplify this whole situation, assume there's only one target, only one track. Okay. So what happened is that initially this track is empty. Okay. So then say this is the time axis. So you get from T1 and say T2, T2 and T2. Okay. So at this point, I get the first update of the track. So I create the track. I create the track one. Okay. So at this point, not this one, like so you have I would say X1. Okay. So when I get the first update, this one is creating a track, maybe the copy of that. Okay. So next time when I get this measurement, somehow I update this. Then when I get this, I update this. When I get this, I update that. Is that clear? So the global one has this. This is a tracker. This global tracker has a global track. It will update this global track with the local one. Okay. So like if I, because instead of going through the slides, this is the basic I think you need to understand. Let's see, my global tracker has something like that. And the local one, as the next time it says somewhere here, then based on the global one and the local one, I will extend this to there. And another one gives somewhere here. then maybe I will extend to this. Okay, this green and black are the tracks from other nodes. This is the global one. Okay, so we are going to update. So clear? So that is the memory. So the ID, you don't use ID. This ID could be 10, this ID could be 3, but this ID could be 1. So we don't use ID to associate. We are going to associate these two tracks and do it. Then, for example, the following step, you have a black here. As a first thing, you do the association between this and this. Okay, first you decide this goes with this. Then you update. Are you okay with that? Yes. Okay. So if you understand that, I will simplify this problem further. So you have a radar here and another radar here. So far, I was talking about the tracks in both of the coverage. Okay. Now assume that is not the case. The only target is here. What will happen in this case? In this case, only this will report the track. That will not have any track. Is that clear? Now, so initially, the central one is empty. Whenever this give update, we have X at 1 and 1. Okay. When you go to this next time step, okay, so you are going to get this blue one again. So I will repeat that. So for this case, so at k equal to 1, and this has this. Okay, then you do the prediction. And say that is like this. Then the update comes here. Okay. So how, like now what do you say about this? Are they independent or dependent? Originally I said we assume independent, right? Are they dependent or independent track? Dependent, highly correlated, not dependent, highly correlated, right? Because it's the same measurement, same track comes here, right? That way, so if you fuse this, ideally what do you want to have here? Ideally, updated track should be, ideally, the updated track of this one should be equal to the X at 2 by 2 platform 2. Are you okay with that? Because we don't have any other information. Only this is the one sending, keep on sending. So the central track update should be same as that. Because we don't have any new information to modify this. We are want to do fusion, but in this case, fusion is only there. So if you do the fusions, you can't do better than this line. Correct? But if you assume they are independent, and if you do the fusion, ideally, this is what happens. If the time k, if the covariance of this is say something like that, but your fuse covariance will be something like that. Because you assume independent, so that you assume it can bring more information, but that is not the case. Because of that, when two tracks are correlated, assuming independent, it's going to create problem. You can keep that in mind. So with memory fusion, that is the case. So two tracks are highly correlated. Mainly so you can think this way. These two are not correlated. But the one we not those two. Let me see. Let me think this. So you track the one, track the two, and this is a fused one. So this tracker and this one, you can say these two are not correlated, I'm okay with that. But if you have something here, you can't say these are uncorrelated because this information is already used in that tree itself. So that way you can't use that again. Okay? It may be a little complicated, but please think and try to understand this part. So correlation is the biggest challenge in track to track fusion. Okay? Anyway, if I repeat this, fusion without memory, sorry, I don't want that. Fusion with memory means in this approach, a global track is maintained and updated whenever the data comes in. Okay?
Just little bit 5 minutes can I take from your session?
Yeah.
Just I'll distribute certificate draft copy. You take your name, application, everything. If anything you want to change, write it by K. We'll make this soft copy. Because if today we don't do, we cannot give certificate tomorrow.
Okay,
It needs lot of signature.
Okay.
Like dean and all those things. Okay. Just 5 minutes. So we take a signature from okay. This is all right. This is class. Once they connect them, they get money. And get it. Then we need to link them to you correct it by pen. Correct it. You are done. Right, anybody.
Okay, let's continue. Keep in mind that so whenever we maintain a global track, so it's going to introduce the COVID, like, well, let's like, okay, because just to repeat that. Let's say this is the first time I send it this information to the globe. Okay. So then this and the global and this should be the same. Are you okay with that? Because there's copy of that. Now we go to K and we go to K plus 1. Let's say there's no association at this point. Okay, there's no measurement from the for some reason there's no more measurement for this. What is this one? This is a predictor covariance, just a predictor covariance, nothing else. Right? Now, but it sends again to the global one. In the global one, the normal approach is that you predict this to the time, then fuse both of them. Right? That's the idea, right? So global one, you predict to this time. The local one sends something. If you assume independent, you fuse some. But in this case, this and this are exactly the same. You understand that? This is also prediction. That is also simple prediction. Then the correlation is 1. If you fuse this, for an example, if this is P equal to, like, scalar case is 10, then this predicted is 10. The fused one should be 10 as well. But when we assume they are uncorrelated, and if you fuse it, this becomes much smaller than 10. So that becomes a problem, right? So you estimate become optimistic here. Okay, so that is, this is a simple example showing that the tracks from the local one and the tracks on the global ones are highly correlated. Okay, that is why we want to go for track-led fusion. I will discuss about that to eliminate the correlation, reduce the correlation or eliminate the correlation before you fuse. Okay, keep that in mind. These slides talk about how to do the cross correlation term, but I will talk about it, but please don't follow the step. This is pretty hard in my, I have an implemented tracker equation. I never use this, okay? I will not recommend this because calculating the cross correlation is not an easy task. Okay, so that is really, really hard. So we are going to go with different approach to handle that. But this one talks about how to calculate cross correlation. Use it. So this one says when the tracks are dependent, correlated. Okay, I already explained something where it's correlated. So common prior information. If two tracks use the same common information, that also introduces correlation, but we can ignore that, but that can happen. Duplicate measurement sequence. For an example, a tracker, this is another tracker, they use the same that here and there, then the tracks produced here and produced here are correlated. Okay, keep that in mind. If the same measurement used here and there, then these two tracks are correlated because common information is used. That is another way of having that. And they say common prosomal. These are kind of little advanced stuff, so you can ignore that. Same target. Yes, it's a same target. Yeah. So, but this common duplicate measurement sequence is this. Like, I think usually I don't allow this to happen, right? So this can happen if this is the case. Let's assume that assume this case. Okay, so this is that, this is that, this is that, this is that track, track, and track. Okay, so we are talking about track to track fusion. If you allow this kind of connection, these two tracks are always correlated because the same measurement is used in both tracks. That is why in the next, so this is really hard to handle. Usually we don't allow that. Same sensor connected to two nodes, I don't allow because that becomes hard. Okay, so if this goes with this, then these two are highly correlated. So when you do the fusion here, you have to handle the correlation properly. So as a first thing, we remove this. So that is not the reason, but we say that you have a local track, then you have a central track. Even though central track is not using the measurement, but you can say that these three measurements are already used here. Okay. Then next time, when you send this track, this uses actually Z1, Z2, Z3, and Z4. Right? So we predict this, that this one already used Z1, Z2, and Z3. Okay, so this information comes from these three measurements. This new information comes from combination of these. You see that there's a common measurement in both of them. This is a duplicate sequence you can think with. The local one is updating with the sensor and communicate here. Even though their measurements are not directly used here, when this update is done, this track has the information from these three. When you go here, this has only three information. This prediction, already you have this information as well. So this is a combination of all four. And when it comes here, these two are already correlated. Because duplicated sequence is there. If you want to eliminate the correlation, somehow you have to cut this. Or you have to change this to a different one. That is called tracklet. We will talk about that. We will form a tracklet such that these three information will be removed from that track. So then you can say they are independent. Okay, there's no common measurement information shared. Okay. This slide mainly talk about what I mentioned, like when you communicate and that introduces correlation. Okay, I will skip this as well. I'm going to skip some of them because this is a cross covariance estimate. In practice, I wouldn't recommend this because if you look at this, finally, so you have two like this and this. If you want to find the cross covariance between these two, in order to find the cross covariance between two of them, you need to this is one, first of all, this equation is complicated. Other one is that you need to know about the weight, Kahneman filter weight they used in the local node. So in order to calculate this, if you look at this. So what we do is, this is the tracker 1, the tracker 2. So you communicate the tracks and then you calculate this cross covariance over here. Okay, the cross covariance is calculated here. This WI is calculated here. Okay, these are the weights that use the Kahneman filter in this node. That's a weight we use the Kahneman filter here, and we find the cross correlation here. In order to do that, in addition to sending X and P, you have to send W as well. Then you lose the benefit of reducing the communication load because you have to send additional information. Then the communication load increases in order to do that, but it's complicated as well. So that's why I said that. So this is a way to do that, but I wouldn't recommend that. Okay, so next, track to track association. I already talked about simple approach. But if you want to handle properly means this way. See, you have this, and this, and this. How do we do the association? Right? By looking at this, can you associate? You can't. Right? It's not an easy problem to associate. Right? We don't know whether this goes with that, this goes with that. We don't know. This is the real complicated data structure problem. Earlier, I was talking about this case. That is easy, right? So like here and here. So you have here, here, and here. This is an easy problem. That's what we talk about. This is like a nearest neighbor approach in which, okay, this goes with that goes with that, this and you, this is it. That's fine. But this is complicated. This is like a multi-target tracking data association. So that can be formulated as an assignment problem. In the measurement fusion, we call it as multi-frame assignment. We would use a similar approach in this as well. So what we do is, we will form this as an assignment problem. Tracker 1, tracker 2, for the central tracker. So you will have all the trees like this, all the possible branches. You consider as you write it as a possible branches and find the optimal branch that minimizes the total cost. That is a multi-frame assignment. This is a multi-frame assignment. Okay. This is multi-frame assignment that is used in the normal single target tracking problem as well, single sensor tracking without track fusion. Even in the single sensor tracking, I mentioned that one of the algorithm is MHT or MFA. Similar idea can be used. Okay. So in this case, what we do is, so we have S trackers, but if S is 2, then you just consider 2 of them. I explain only 2 of them. But if you have S trackers, you want to find, this is the branch I was drawing. Okay, this one is the branch I was drawing. And this is the cost of that branch or likelihood of having that branch. And these are the constraints, says that it's at least better to know this kind of assignment problem. Whenever you want to use, you can use it. Let me explain with a simple problem. Say track 1 and track 2. So always we have a dummy. These are called dummy tracks. Dummy. Okay. And then say I have 1 and 2, 1 and 2, or 3. Okay. So we have 1, 2 tracks from this, 3 tracks from this. These are dummy. Always we add dummy. Dummy means missed or 4 tracks, something like that. Then one feasible association might be this and this. That's a feasible association, right? That means this track goes with that track goes with that. Or you can have this and that. That is fine. Sorry, this is not fine. This is not fine. One track cannot go with 2 of them. That is not allowed. Okay, this can be allowed. This is not allowed. Okay. 2 tracks from this cannot go to the other tracks together. That's not allowed. But for dummy, this can goes like this. What is the meaning of this? Can somebody explain that? The meaning of this? So this one, basically it goes like this. If you have something like that, it says none of them is associated. No association. Okay, so this track is associated with the C dummy track of that, no association. This track is associated with dummy, no association. Similarly, this is associated, none of them is associated. That could be like this. And this is here, here, and here. Then you would end up with this kind of situation. Okay. Okay, so this dummy is there to show that no association. If it goes here, no association, but there's no constraint on this. You can have multiple connection to that, but this point cannot have multiple connection. Okay, that is the multi-frame assignment formulation like that. Then if you want to put those in constraint, then that is what it says. For a given node, if you take all the sum of these branches going through that, for an example, in that case, for an example, if it's like this, it says that we can't have these two solutions together. We can't have this and that because two of them are going together, right? So that is not feasible. So that is why it says if you add all these, only one of them, one connection can go through that term. Anyway, this itself is a really complicated optimization formulation, but I use this in many cases, resource management and several places. This kind of optimization problem comes. Okay, so then if you write a paper, I would say knowing the multi-frame assignment is important. Okay, but if you want to implement track to track association, you may not need to do this way. You can go with the kind of global nearest neighbor approach, like one after the other. Suboptimal, that's okay as long as your targets are separated or tracks are separated. Okay. Then this talks about the course. I'm not going to talk too much about that. So then with the optimal fusion, we will use this cross covariance term. But I recommend that don't worry too much about this because we are going, maybe this might be an optimal approach, but finding all these are not really feasible in the real system. So I would go with some suboptimal approaches that we are going to discuss now. Okay, this is an interesting observation, so I will explain this slide. Impact of cross covariance. Okay, let's consider two static estimates, a scalar value. Okay, you want to estimate a scalar value, and both of them have estimates, and both of them have the same covariance P. Okay, so one estimate says it's here with a value P, other one says here with a covariance P. Same covariance uncertainty for the estimates and this and there. And if you use this, maybe you will end up with the middle. Correct? Okay, the problem is this. So the actual value is say a scalar value 5. You don't know that value, you have an estimator. One says my estimate is 4.6 and my sigma or P covariance is 2.1. Okay, and the another estimator says my estimator is 5.1 and my covariance is again 2.1. Okay, so in this case, what is the fused estimate? Fused estimate, because the covariance is the same, so fused estimate should be 4.6 plus 5.1 divided by 2. Are you okay with that? Okay, now let's say I reduce this. I reduce this to say 1.0. What happened to the estimate? Pardon? So the estimate, so if it's 4.6 here, 4.1, earlier it was here, now it will goes towards that. You did more weight to that, right? That's the idea. Okay. So that now it says that. Now in this one, it says that, so that's what it says, right? the fuse estimate is going to be half because equal. Both of them are equal, so we are going to have that. So the variance of this is going to be this. Here, this is the correlation term. Initially, we don't know anything about the covariance, correlation. If you assume the correlation is 0, if you assume the correlation is 0, then what happened? The PF is going to be P by 2. Are you okay with that? Covariance is half. But if the covariance, no gain in fusion, so if the correlation is 1, so if the correlation is 1, what is the PF? P. Right? If the correlation is -1, then the PF is 0. So if you ignore the cross correlation, so you are going to report P by 2, but the actual could be P to 0, right? So when you ignore the cross correlation, your one could be optimistic or could be pessimistic, depend on the actual correlation. Okay? Can you give me an example in which P correlation is 1? What does it mean? Correlation 1 means what? Let's say the actual, let me repeat that. Okay, actual value is 5. The first estimate, x1 is 4.6. What is x2 if the correlation is 1? If the correlation is 1, that's also going to be 4.6. That's why you don't get any benefit out of it, right? So that way, covariance won't reduce further. That is the correlation 1. Correlation -1. So if it is 4.6, that is going to be 5.4. There is negative, opposite of that, right? But anyway, these are like ideal cases. You won't have this kind of a case, but here what we say is that you can't simply ignore the correlation. Basically what we want to say is that you can ignore the correlation, but you should know the effect of it. When there's some correlation, when you ignore it, you are introducing some issue there. Your covariance could be optimistic or covariance could be pessimistic, and over long run, they may introduce new problem. Okay. Okay, now this is a concept that I'm going to introduce, track length. Even if you understand like whole thing, at least you should know the meaning of track length, because so you know track, right? Everybody knows track. Track means what? X and P. That's what we communicate, right? We communicate if X and P. If you want, we communicate ID as well. Send it to other side, we send it. Then we talk about AMR, associated measurement report. Then we send that and up. Correct. Now we are going to talk about track length. Okay. I think the one thing that I didn't talk earlier is that this is time. So we have a radar. Sampling time is 2 seconds. And we are communicating that track. What is this gap? Anyone? 2 seconds. Any other answer? Usually that's not 2 seconds. Definitely it's not less than 2 seconds. I'm okay with that. But usually it's not 2 seconds. It could be 10 seconds, 1 minute. Depend on the application. Okay. So we don't need to communicate because our objective is to reduce the communication load. Right. Okay. If you can send every 2 seconds, that's better. That's much better. So you get a better estimate at the global one. But if you want to reduce the communication load, you will send only like once in a while. You may get multiple updates, but send once in a while. Correct? Usual communication is like the track to track question. Usually, this is how it works. Even if the sensor sampling time is 2 seconds, we will update after few frames. And also, it may not be constant. You don't think that always 10 seconds. That is not true as well. So this could be 10 seconds, could be 20 seconds. That can be. Okay. So there's no constraint saying that, oh, this has to be fixed. No, it's about sending information whenever you have something. Okay. Okay, keep that in mind. Now we are going to talk about tracklet. Idea of tracklet is not that hard. Okay, so let's say the radar sampling time is 2 seconds. We communicate here and here. Okay, and I said that when we do the fusion, this is centralized. Centralized fusion, we update here. Okay, after this, you have say the information say 1 to 5. Okay, k equal 1 to 5 because time step is 2. So 5 measurements are used to send and update. So this one will have information from SAT1, SAT2 up to SAT5. Are you okay with that? All these 5 measurements are already used here. Then when you send this, this information contains 1 to 10 k value. Is that right? So now, as I mentioned earlier, this is highly correlated because this 5 already here as well. So they are correlated. Right? The idea is to remove this such that instead of sending track, so this is track. If you send a track, this is it's what is going to happen. So instead of that, I am going to send a tracklet that will have only the information K6 to 10. Please try to understand this one. Okay. So what I said that like if we send tracks at this point, I have information from like this 1 to 5. All the information comes here, update. So updated state already contains this information. Then when we go to the next time, we send the tracks. So that track contains information of 1 to 10. All the information are there. Now if we compare these two, we want to fuse these two. There's a common information here. 5 is already there and 5 is there. That introduces correlation. That's all. So now what we want to do is instead of sending this track, we want to send a tracklet. You can consider a modified track such that that have only information that we got here to here. Okay. Don't you see that? Reason why sharing is not shown here. Okay, yeah. By saying that we want to form a tracklet, that's something similar to tracks, but that use only the information from here to here. So that way, so now when we fuse these two, you can ignore that there's no correlation. So when you fuse these two, then there's no correlation. Correct? That's the idea of tracklet. So that you send the new information. You send the new information that we get after the last communication, such that that new information is correlated, uncorrelated with this, so you can update easily. Okay, that's the idea. One simple way to form the tracklet is what you can do is you communicate here. So in that, this is one way I'm saying that, right? In the local tracker, you have two trackers, tracker 1 and tracker 2. Two trackers are in the same node. The same node, you have two trackers. This is the normal tracker. So normal tracker, you keep on updating here. Okay. So this tracker 2, what we do is we restart at this point. So then when we communicate, we send the new track, then we restart here. You understand that part? So you have a tracker that tracks up to this, send the information, then restart the track. That means this information is lost in that. So it's like a restarting in one point initialization and do the filtering again. So that way, so this new information, this information will be captured in that track and we don't have it here. So that way you eliminate the correlate. So again, it could be X and P. Again, it could X and P, but it's a restarted track so that X and P contain all the information from here to here. This is like intuitive way of thinking, but I will go and show the equation of how to calculate the track length. But intuitively, this is what you would try to do. You want to create the track such that this information is not used anymore. Then this is uncorrelated with the central one, you fuse easily. Okay, but you have to consider several things when you restart. The data, maybe you do the data association using track 1, but only the filtering is restarted. Right? You have some connection between those two. You can do that and communicate and fuse. Okay.
But I have one question. If we restart the tracker again and again, the covariance will increase. There might be some convergence issues.
Convergence issue. What kind of
Covariance that we are calculating. We sliding the covariance estimate. Will not converge better if we restart again.
So the idea of restart is to capture the new information that you have. So if you doesn't converge, that means the new information is much less, right? But so this tracker will be we keep on running. So that has a whole tracking, right? This one is about filtering. Okay, so you are saying this, right? So the covariant is like going here or like this way. So if you have a K and the covariance usually goes like that. So what we try to do is we communicate at this time, we go up here, maybe like that. Is that right? That's what we are trying to do. So because this is the new information that we have. Okay. So that means like covariance should be large, then the fusions should handle that properly. Okay. So that this is what happens. Like when we restart covariance, that's what we want because uncorrelated means the new information is that. If you think about CRLB, this is the information that we get from the new measurement. So information should be less. Yeah, that is a covariance should be large. Okay. Okay. So now again I repeat that a tracker can send tracks or tracklet. Okay. So that we said that if we find the tracklets, we can handle easily. But practically, no one will send you tracklet to you. Okay, because they will send the track. They don't care because as a human, we will pass our burden to someone else. So similarly, I send the track. You do whatever you like, right? So usually, what we do is in the central one, central fusion, we get the tracks. We get the tracks. Idea is to before we fuse, using these two, we find the tracklet. Then fuse. Okay. So what we want to do is that tracker send the track and tracker send the track. From these two tracks, you try to find out the new information that you have. Okay, that's the tracklet. So you want to from these two tracks, you want to extract the tracklet, then use it. Rather than you ask the tracklet to be calculated by the local tracker. You can do two things. You can ask the local tracker, so please calculate the tracklet and send it to me. In the other case, you send the tracks, I will find the tracklet, then I will fuse. Okay. Second approach is the most feasible approach. Okay. Or if you think this way, like for example, so you have a covariance like this, and you are communicating here. So the predicted covariance, we simply predict. So this is 10 seconds. If you simply predict, it will be like that. Okay. But with the tracker, with the doing tracking, you get something like this. By using these two, you can find a new information. If you think about CRLB, assuming you know CRLB, J equal to Jx plus Jz. Okay. So this, using that, you can find the new information that we have in the COVID. Well, that's the basic idea. Okay, again, sorry, what you need to know about tracklet is a new way of representing a track such that that track contains information only from the measurement that are obtained after the last communication. Okay, that's right. Okay, that way to eliminate the correlation with the other trackers, other tracks, so that we can fuse it. Let's go through these sentences so that may be easier. Estimating cross covariance within tracking may require too much communication and low tech computing. Okay, we already talked about that. That's all. So this is a tracklet fusion is an efficient way of doing it, right? So this is not correlated with any state estimation of the other data. That is an important part. This is not correlated with any of them. And this is, please read this. Okay. So this is what I was repeating. It is equivalent to a track for a target based only on the most recent measurements since the data from the tracker was last transmitted for that particular target. Okay. Okay, now there are a few methods to calculate tracker, not one method, multiple. So there are three methods that we are going to discuss. Okay, so let's start with the first method. This is called inverse unmultiplier based tracklet, in which input is this, input is this, and this actually. So now you are going to convert into tracklet. Okay, these are the facts. From that you calculate the tracklet. Then you send this to the fusion node, and they will use it. Okay. So if you look at this equation, that's a simple prediction without noise, no noise involved. You use a prediction. So basically, if you are here last communicated, do a simple prediction. Okay. Then don't worry about the derivation. And if you look at these, finally, we calculate this as a function of the predicted state plus some A and then gap. Okay. It's a predicted state versus the updated state and difference and so. One thing that you need to notice that in order to do this factor calculation, we need to do this. Okay. So this is an important part. Okay. In order to use this inverse convolutional based tracklet calculation, this is a tracklet. In order to do that, you should be able to find this inverse. Okay, what do you think about this? Do you think that we can find this inverse all the time? So this is basically this is this. Okay, so you have P, say 5 out of 5, then you have P 10 out of 10, and now we are talking about P 10 out of 5. Okay. Now it says that, so can we, if you find P 10 out of 10, can we invert this? What do you think? It would be like, can we invert this all the time, or there will be a problem? We can't do that under certain conditions. Usually, which one is larger, this or that? This is large. This is predicted and that's the update, right? So this covariance is always larger than that. That's fine. But it may not be invertible. For an example, I change this to 6. Okay, instead of 10, I change this to 6. This is 6, and this is 6, and this is 6. If you do this, the new information that we get is only about the position. We don't know anything about the velocity because we use only one radar measurement. So the tractor will not have an information about the velocity. Because of that, this cannot be inverted. If you have two that like that's what it is. Like if you communicate at every time with, then this approach cannot be used because that's not invertible. This is only works if we get more than one measurement between the communication, then you can invert this and you can use this approach. But if you get only one or less than one measurement in between the communication, this approach will not work. Okay. So this is what it says, right? So this cannot be used if there's only one measurement reported in that interval. But this is true for radar measurement. If it's an angle only measurement, then what do you think? See, if it's a radar, this method cannot be used if there's only one measurement. If it's an angle only measurement, for how many measurements that we need? Even 2 is not enough because 2 can be used to find the position, not the velocity. So it could be 3, right? So you may need 3 measurements in order to capture the velocity and so on, right? So you need more measurements in order to use that. Okay, this is another approach because of that limitation. So in this one, again we do this, and eventually this is a different notation. This becomes a triplet. If you look at this, only inverse that we have is here, but this is always inverted. Okay, there's no difference. This is the inverse of the predicted covariant. Predicted covariant is always positive semi-definite, so you can find the inverse. So no problem. So this approach can be used under any circumstances. But in my practical experience, what I found that even though all they like says that it can work, what I found was that most of the time my tracker end up with the covariance matrix that cannot be inverted. So when you do developer trackers, not only for tracker coefficient, even in the normal case, you have to consider a situation in which one of your eigenvalue can become negative of a covariance. Right? That's due to machine precision. Usually that's the case, right? Due to machine precision, when you have tracks, one of the tracks covariance becomes non-positive definite matrix. Then your code will crash. So you have to handle that somehow in order to avoid crashing. That is important, right? So maybe you check the eigenvalue. If it is approaching negative value, you do something to fix that, or at least kill that track, or do something. Similar to that, in the tracklet, what I found is that even though it can work, but I found that in some cases, I get negative input. Negative information was the problem. Negative information means because there are mismatches, right? The mismatch comes in this. That's what I always say that track to track coefficient is the harder problem. The reason is that the local tracker may use concern velocity with Q. One. In the global tracker, so if you are ever developing a simulation, you know everything. But in the real system, somebody will send the tracks. They will not tell you about the Q1. Okay? They won't tell you. Then you may use a Q that may not be same as that. That introduces a model mismatch in the prediction and information calculation and so on. That is a real problem. The real world problem is that. Okay, so you need some way of handling this mismatches. Otherwise, you will end up with this non-negative covariance issue, and somehow you have to handle it. I'm not providing the solution, I am at least talking about the problem. Other real world problem is that in order, the old algorithm I explained, we assume these two are communicable. Okay? But in some cases, they will not provide the speed. Okay, so because they want to reduce the communication, they will not give the speed. You do whatever you want. That is hard. I don't know what to do with that. So P is like this, right? Say usually it's 4x4. Sometimes what they do is they make you only the diagonal element, nothing else. Reduce the communication, they give the diagonal. If they want to reduce further, they will say good, bad, something like that. So scalar value, like so. This track is okay. This track, maybe for an example, you find the race of this, race of that, and you do some thresholding and say, okay, this quality of the track is good. This is bad, something like that. Then you have to do the fusion. These are the real challenges. I don't think any paper talks about that, but in real world problems are like that, right? So you may need try to reconstruct the covariance before we fuse, but these are the challenges. Okay. Okay, last one is the information filter form. I don't know how many of you know about information filter. Information filter is another way of implementing the Kalman filter. Okay, that's not about passive activation. Information filter can be used instead of the Kalman filter in an inverse form, right? Here idea is the same. So you want to use an overlay. This is the new information that we get. This is what I was talking about. This is the inverse of covariance, the new information that we have at this point. This is the information that we predicted. If you subtract this, that will give the new information that we get from the measurement. Okay, these are the new information that we get. And corresponding, I can't call this as covariance. I don't know the term that we use for that, but that corresponding information uncertainty is given by them. Okay, so we talk about three approaches. After this, what we do is once we get the tracklet, you can treat this as that with hx plus omega. Okay. So once you get the tracklet, instead of considering this as a track to track association, you consider as a track to measurement approach. Let's say let track to measurement association, and the measurement is that measurement is the track. Okay, let's think that. So we want to global tracklet is a measurement. We want to update. Now what is a measurement? Now we want to talk about that, right? So earlier we talked about this inverse Kalman filter form. In that one, in this one, this is a Z, this is the R, okay, or maybe here, right? Okay, this is Z, and this is R, and this is the H. Okay, so this is the corresponding. So that is R. That is R. And H is I. Okay, that's what it says. For this method, this is Z, this is R, and H is I. And similarly for this, H is PA. Okay, so this is H. So different equation has different H and different Z value. That's it, right? Once you know all these, what we do? This is a normal Kalman filter equation by substituting this. Instead of H, we substitute B, and you get this. If you substitute B equal to I, you get that. So this step is straightforward. This is nothing new here. This is a normal Kalman filter. This is a normal Kalman filter. As long as you understand that for this inverse Kalman filter, H is I, Z is Y, everything small y, and capital R is capital Y, then you get it. Okay. And in this case, H is B, you get it. Okay, that's all about the tracklet. To quickly summarize tracklet, tracklet is an equivalent you can say equivalent measurement that summarize all the information that we got from the last update. And that is uncorrelated from the all other tracks, all other track output. Then we can form that as a pseudo measurement, comes from a sensor rather than a track. So we consider that as a measurement that comes from a tracker or sensor. Then we use that measurement to fuse as a normal, what we do with the measurement level fusion rather than the track level fusion. So by doing this, we eliminate the correlation process. Okay, so I would recommend this. Okay, I would recommend using track level fusion. I don't have any concern over that, but you have to be careful about the inverses. Okay, so inverses, finding inverses, you may end up with some issues somewhere. So in the code, you have to handle that to avoid crash. Okay, so this is the last topic for today. I don't only few slides. This is my favorite approach. This is a suboptimal one, but fortunately, it will not create any crash. Okay, at least from my experience, doesn't make that invertibility issue most of the time. But it may not be optimal. That's why some of the people who are really mathematicians, they don't like this approach. But I prefer this over all others because this is like robust one. Okay. So here, like I'm not going to talk too much about the math, but I will talk about the intuition. Covariant intersection says that if you have a tracker like this, another track like this, idea of fused output is should be like this. You understand that, right? So if it goes here, then the intersection, right? So it should be the intersection. The covariance should be the intersection of that. Okay. So that's a basic idea of cross covariant intersection. It says that from the name itself, it says that you find the region where it intersects. Ideally, you want to have only this region, but we can't do that because we approximate with the Gaussian. So we will go with something, the smallest possible ellipse that covers that region. Okay, so then you might ask, what is the problem with it? Why people don't agree with it? The reason is that the reason the people don't like this is this. If you remember the scalar problem, we said that if you have P and P, and if you fuse them, there should be P by 2 if there's no correlation. You remember that? If there is no correlation, if you have two estimates, and if you fuse the same covariance, if you fuse them, the updated covariance should be P by 2. Now, if I repeat that, if this is a covariance, another one reporting like similar covariance here, and if you fuse this, update should be like this, if there's no correlation. Okay? But in the covariant intersection, the upload will be same as black and blue. Okay? Because covariant intersection is just checking the intersection. So instead of red, we will get this blue as if I update one. So that way, covariant intersection is always pessimistic. In my opinion, being pessimistic is much better than being optimistic in many sense. Okay, that is why you lose some optimality, but it will not create any problem. But if you are optimistic, you will lead to track losses. If it is pessimistic, it's not that bad. Maybe if you are a messy, if you instead of going here, if you're pessimistic, maybe you are a messy might be something like that. That's okay. I'm okay with that, right? Anyway, this is like my personal opinion, right? Different people have different opinion on it because it's not theoretically correct, but I am talking in terms of my experience, and I like this because I'm okay with that instead of having crashes and some other additional issues. Theoretically, people might say, okay, tracklet works better because you simulate everything matches, so it's fine. But in real world, when we have so many uncertainties, so this is robust. Like always like that, but robust, but you won't have any problem. Okay, but anyway, as long as you understand it, covariant intersection could be pessimistic in understanding phases, but may not be optimistic, but it intuitively makes sense. Okay, so that is the basic idea of covariant intersection. Because there are not many papers, that 1 or 2 papers is there, that's enough to implement covariant intersection, but I would say it's not widely advertised, but I personally prefer a lot. Okay. So what they do here is that, so finally, like whatever I mentioned comes to this form. So they have a weight that those weights are calculated such that the updated covariance will be intersection of both of them. Okay. I think I don't have an equation to calculate the W here. You may need to refer the book or the paper to calculate that W. Okay, because that involves some optimization. So I don't have that. So by solving that, you get it. I think which paper is that? In the bottom one, I will show that. Okay. The last thing, okay, last point about summary about track to track fusion. I mentioned this, right? In some cases, covariance may not be available to you. Then the fusion is hard. Okay, you have to come up with something. Other issue that I mentioned is the motion model mismatch, right? So you may assume something in the central node and the local one, they may use a different motion model, right? And the worst case could be in the tractor, they may use IMF. And in the central one, you use the Kalman filter. That creates even more problem. Okay? So you have to keep that in mind. Okay? Okay, last one is the heterogeneous fusion. I'm not going to talk about that. Heterogeneous fusion in which you want to fuse x dot y dot versus r dot theta dot. This is a harder problem and the cross correlation could be negative or positive. And in that case, ignoring the cross correlation might be a better option. But usually I don't do this kind of fusion. And if you want to do that, you want to read more because I didn't teach anything on that. Okay. Okay, that's all for today. And I think original plan was to have a 1 hour of resource management, but I don't think we have time. So tomorrow, I think we have only 2 hours lecture, and after that we have the quiz, I believe. So tomorrow my plan is to talk about the resource management part. Okay, but in the tutorial today, we will continue the remaining part mainly